Hello and welcome. Dear students, today we are going to discuss an important topic, that is human impacts on the hydrological cycle. As you know, the hydrological cycle or water cycle describes the natural processes of water storage and movement in different subsystems of the hydrosphere. The hydrosphere defines the combined mass of water over, on and under the surface of the earth. About 97% of the total world's water is stored in the oceans. The natural hydrological cycle is essential for sustaining ecosystems, agriculture and human societies. However, human activities have fundamentally altered the components of the cycle. The impacts of human forcing vary significantly across regions and temporal scales. They have reshaped the fundamental structure and functioning of the hydrosphere. These anthropogenic influences have intensified since mid-20th century. This has created cascading effects and thereby altered the ecosystems, agriculture, water availability, its quality, climate processes and human societies globally as well as nationally. Therefore, understanding these anthropogenic impacts on the hydrological systems is essential. This module examines the human impacts, the driving factors and the modeling approaches of human induced changes on the hydrosphere. Some case studies are also provided with respect to India. Let us discuss them in this lecture. Human impacts on the individual components. First, atmosphere. The human driven climate forcings have altered the atmospheric branch of the hydrological cycle. Globally, significant modifications have occurred in cloud formation, atmospheric moisture and precipitation patterns. These changes mainly occurred after the Industrial Revolution. The land, air, sea thermal interactions have been modified that suppress monsoon circulation and reduce rainfall over South and East Asia. In contrast, the moisture holding capacity in the atmosphere has increased due to warming. According to the Clausius-Clapeyron scaling, an 1 degree Celsius of increase in temperature increases water vapor by about 7%. The earth is receiving more intense precipitation. Extremes like cloudbursts and flash floods, while shifts in circulation patterns led to drought elsewhere. The varying ocean atmosphere modes, for example, El Nino Southern Oscillation or ENSO, continue to create strongly heterogeneous precipitation patterns. Similarly, long-term trends show that Indian summer monsoon has declined by about 5 to 10% since 1950s. Large scale changes in surface energy have reduced monsoon precipitation in India. The break monsoon spell is generally a dry period during July to August in India. Its frequency and duration have increased and suppressed rainfall. Additionally, the land atmosphere feedbacks have also indirectly affected the atmospheric hydrology. Altered surface energy balance has modified local convection and moisture recycling. There are also direct changes in evapotranspiration, humidity profiles, cloud formation and storm development. For example, reduced evapotranspiration from vegetation loss suppresses convective rainfall, whereas irrigation increased atmospheric humidity has modified precipitation. Studies from major Indian cities indicate that urban heat intensities have increased the localized and short duration rainfall by 10 to 25%. Reduction of surface albedo, evapotranspiration, moisture recycling and reduced water vapor fluxes are reported in the Western Ghats and Himalayas. Second, surface water. The surface component of the hydrological cycle have also been impacted by several human factors. Reduction of canopy interception by up to 35% is reported to have increased surface runoff coefficients and reduced infiltration in many parts of southern India. This has increased flood peaks in watersheds by 40% compared to the forest basins. Soil sealing due to urbanization increases the runoff coefficient by nearly 18% and decreases infiltration by 30 to 40%. In the European basins, an 8% increase in urban area increased storm runoff by about 3%. In addition, changes are seen in runoff, lag time, peak concentration and recharge. Studies from cities such as Bengaluru, Hyderabad and Delhi suggest that runoff lag times have decreased by nearly 1 hour. Peak flows have increased by more than 200% and recharge has decreased by more than 50% in peri-urban catchments. Inefficient irrigation causes leakage and canal seepage and raise groundwater levels, leading to waterlogging and salinity. Intensive irrigation increases evaporative losses and reduces downstream discharge by 20 to 30%, particularly in semi-arid watersheds. Reservoirs and dams have suppressed downstream flows and cause evaporative losses. In Punjab and Haryana, reservoir seepage and canal irrigation raises water table by up to 1 meter per year, causing continued waterlogging in about 15% of the command areas. Continuous plowing, crop rotation and mechanized cultivation also modify soil hydraulic properties. In Himachal Pradesh, soil water holding capacity has reduced by 25%. Water is drained from wetlands due to filling and development. Third, groundwater. Increasing disruption is seen in infiltration and percolation that are essential to regulate the downward transport of water to the aquifers. In urbanized cities such as Mumbai and Bengaluru, infiltration has dropped by more than 50% in some watersheds. Farming increases soil bulk density to about 1.6 gram per cubic centimeter in some watersheds. Above this threshold, pore spaces collapse and infiltration declines. This has reduced infiltration by more than 50% in intensively farmed watersheds. Such practices have destroyed natural soil structure also. Transformation of dry croplands to paddy fields increases percolation and seasonal recharge. Soil moisture has reduced and springs have dried as observed in the Himalayan regions. The groundwater storage in the aquifers of Gangetic plains is reducing at a rate of about 2.5 centimeter per year, while as over much of the northern India about 450 cubic kilometers of groundwater has been lost. The base flow in some Himalayan streams has reduced by up to 50%. The withdrawals are so huge and fast that natural recharge is unable to replenish this in some places. Similarly, intensive pumping has lowered water table and produced measurable storage declines across the world. Pumping raises evapotranspiration by 10 to 25% relative to the natural baselines. Consumptive use, also known as evapotranspiration, is the amount of water that is stored in the plants and animal tissues and is no longer present for use by humans. This has reduced dry season stream flow by up to 40% in some catchments. Additionally, a reduction of groundwater recharge and downstream flow has been recorded over recent decades. Hydrological models reveal that such impacts are severe in regions with dams, high population and intensive irrigation. Similarly, the residence time of water has been reduced by a significant factor. It is the average time a water molecule stays in any reservoir of the hydrological cycle. It naturally varies from few days, for example, in atmosphere to even millions of years as in ice sheets. A few studies from India found that deep groundwater is rapidly recycled. This releases some deadly chemicals faster than previous rates. Fifth, impacts on water quality. Several human activities have significantly degraded the surface and groundwater quality. As per the Central Groundwater Board, nitrate levels often exceed the drinking water threshold of 50 mg per liter in some parts of India. In parts of Rajasthan, excessive nitrate above 200 mg per liter caused blue baby syndrome in infants. High amount of nitrogen and phosphorus in streams and lakes promotes eutrophication and bloom of harmful algae. This has resulted in 2 to 4 times higher biochemical oxygen demand than recommended values. Studies suggest that about 70% of surface water bodies in India are contaminated. Carcinogenic pesticides and insecticides are commonly found in water. Several heavy metals, for example, lead, zinc, copper, hydrocarbons and suspended sediments have been added to the water. The domestic wastewater releases chemicals, pathogens, microplastics and emerging contaminants into the water. Groundwater over pumping also adds more chemicals like arsenic, fluoride, etc. due to enhanced water rock interaction. Arsenic levels exceeding far above World Health Organization safe drinking limits of 10 micrograms per liter in parts of Indo-Gangetic Plains and Bangladesh. This has severely affected human health. These changes highlight the importance of pollution control approaches to maintain ecological and public health. Second part is the major contributing factors of hydrological changes. Several human activities impact the quantity and quality of water in the water cycle. Number 1, greenhouse gas emissions. One of the major contributors that have reshaped the atmospheric hydrology during the mid-20th century is the release of aerosols into the air. After industrial revolution, emissions from coal, combustion, metal, smelting and other industrial activities have increased. Greenhouse gases induced moistening and aerosol induced suppression have impacted evaporation and precipitation. Greenhouse gas emissions and black carbon warms the atmosphere. Climate studies suggest that the aerosols scatter sunlight, cool the surface and increase cloud droplet concentrations. Sulfate aerosols delay precipitation formation. India is one of the world's largest aerosol hotspots. Industrial emissions, biomass burning, vehicular pollution and dust are very high in some cities. These have caused a 5 to 10% reduction in Indian summer monsoon precipitation. Biomass burning and pollution in the northern states like Punjab and Haryana releases heavy aerosol that enhance fog formation. Second, deforestation. Forests are lifeline of the earth. For hydrological cycle, they regulate several components and processes. Forests manage the moisture release and root water uptake from soils. However, humans have reduced the forest cover, leading to changes in the atmospheric, surface and groundwater components of the cycle. These changes are observed at local level as well as regional level. In tropical areas, it has reduced evapotranspiration, rainfall and caused drought conditions. In Himalaya, it has reduced evapotranspiration by about 20%. The loss of trees means reduction of interception rates, that is, less stem flow and throwfall from leaves. This increases infiltration and percolation. Soil compaction has lowered infiltration capacity by more than 50% in degraded watersheds of Shivalik hills. This raises water table, causes water logging and increase flood frequency. UN's Food and Agriculture Organization (FAO) reports that the magnitude and intensity of small floods has increased worldwide. The cutting of trees also limits shading and increases atmospheric temperature by about 3 degrees Celsius in some regions. Deforestation in one part of the world, for example in Congo, has impacted rainfall in far off parts like in America. It has modified the carbon cycle and reduced carbon sequestration by plants. This has increased atmospheric carbon by a significant number. It also reduces the amount of water in the biosphere and impacts biodiversity. In the Amazon forests, 50 to 80% of moisture remains in the ecosystem's water cycle. Deforestation also enhances soil erosion by eliminating the soil anchoring properties. Soil erosion in several catchments of Arunachal Pradesh, Assam and Jammu and Kashmir sometimes exceed 150 ton per hectare per year. Due to this, sediment load in the streams and reservoirs has increased. Deforestation increases the risks of fire, further releasing carbon dioxide. Cases of forest fires have been reported in the Amazon, the lungs of the earth. Second, water overuse. Water is abstracted from rivers, lakes, reservoirs and aquifers for human irrigation and industrial purposes. Huge volumes are also drained for thermoelectric and nuclear power generation, mining and aquaculture. Such human processes have modified the natural processes. Precipitation is unnaturally trapped through rainwater harvesting. Water is diverted from rivers and lakes and stored in reservoirs. In river basins like Ganga and Krishna, about 50% reduction is seen in dry season flow. Modern agricultural practices have drastically altered the natural drainage systems. Intensive irrigation has reduced the water storage. Irrigated area in India has expanded by more than 60% between 1970 and 2020. Huge volume of water is pumped for these purposes, depleting the aquifers. Nearly 87% of total groundwater extraction in India is utilized for irrigation annually. This has also increased the cost of drilling deeper wells and impacted farmer income. Studies in northwest states of India suggest a lowering of water table by half a meter per year could increase surface temperature by 1 degree Celsius and generate heat waves. The burden on the groundwater reservoirs has dried wells and springs. The Central Groundwater Board reports that nearly 54% of wells in India have shown a significant drop in water level. Out of them, in 16% wells, the water level has dropped by nearly 1 meter. Continued water spread on the irrigated lands has increased evapotranspiration and atmospheric moisture. Such changes are observed in parts of northwest India and Indo-Gangetic plains. Nighttime humidity and local rainfall have risen. Crop rotation and high organic matter has increased infiltration by more than 30%. Similarly, continued tillage such as in Punjab has reduced infiltration by up to 50%. In Madhya Pradesh and Chhattisgarh, agriculture on earlier forest lands has decreased infiltration by more than 30%. Also, this has peak discharge in the Narmada and Godavari rivers. More biomass, more produced food and animal farms store water and increase its residence time. This water is even exported from one country to another. Water over abstraction has also increased saltwater intrusion in the coastal aquifers. This increases the levels of chemicals and salinity above the standards of drinking and irrigation. Saltwater intrusion in shallow aquifers of Gujarat, Tamil Nadu and Odisha has increased electrical conductivity up to 6,000 microsiemens per centimeter and chloride levels to more than 250 milligram per liter. Due to water abstraction, the rocks are compressed and the overlying material subsides. Global examples show that this subsidence has exceeded 5 meters in parts of Mexico City and California. Similarly, in India, subsidence of up to 5 centimeters per year is documented in parts of Delhi, Punjab and Chennai. A recent research was published in the Journal of Geophysical Research Letters in 2023. It suggests that groundwater pumping has shifted the Earth's axis of rotation by about 80 centimeters or 31 inches in past 20 years. Fourth, natural hazards. Natural hazards such as floods, droughts, cyclones, landslides and wildfires profoundly alter water storage, fluxes and dynamics. Extreme precipitation events increase runoff and cause floods. Floods in turn alter channel morphology, spread sediments, redistribute contaminants, increase turbidity and leads to recharge of contaminated water. In contrast, droughts reduce soil moisture, stream flow and recharge. Severe droughts have significantly decreased river flow and declined water table by meters in semi-arid areas. Cyclones and tropical storms bring extreme rainfall, coastal flooding and led to saline intrusion. Wildfires turn topsoil into hydrophobic layer, reducing infiltration. Landslides redistribute soil and sediments and alter water flow. Climate change also impacts the water cycle by changing precipitation patterns and increasing the frequency and magnitude of extreme events. The exposure of lands once covered under glaciers modifies the albedo feedbacks affecting temperature. Together, these changes underscore the need for hazard-informed and climate-resilient water management. Third part, human-induced hydrological changes in India. Hydrological changes due to human factors have also been observed in many parts of India. Land use changes and deforestation in the Western Ghats has reduced dry season stream flow, infiltration and groundwater table. Urban impervious lands have reduced groundwater recharge. The water systems have also been affected by river regulation, interlinking and dams. Such alterations may alter land atmosphere feedbacks and influence monsoon patterns and change the timing and magnitude of river flow. River interlinking projects have altered natural flow and created ecological pressures in several basins. The Ken-Betwa link, approved in 2022, aims to connect the water surplus Ken River in Madhya Pradesh to the water scarce Betwa River in Uttar Pradesh. There are concerns that it may reduce flow in the Panna Tiger Reserve. Similarly, the linking of Godavari, Krishna and Kaveri may also reduce recharge and enhance erosion in Andhra Pradesh and Tamil Nadu. In Punjab and Haryana, rapid groundwater extraction has declined water levels and lost nearly 65 billion cubic meter of reserves in past 20 years. India is the world's largest extractor of groundwater and pumps nearly 25% of the world's groundwater annually. About 67% of the total irrigation is done by pumping of groundwater from wells in the country. As per the 7th minor irrigation census of 2024, there are nearly 2.2 crore wells in India, including dug wells and shallow to deep tube wells. Intensive abstraction has raised the concentrations of nitrates, fluorides and heavy metals as seen in parts of Punjab, Haryana, Rajasthan, Gujarat, Telangana and Ganga Brahmaputra plains. Human activities dump untreated domestic sewage, industrial discharge and agricultural runoff into the water bodies. As per the Central Pollution Control Board, the water quality in about 72% of the river bodies of India is contaminated and fail to meet water quality standard tests. Fourth is the modeling the impacts on the hydrological cycle. Globally, models are used to study the impacts of various factors on the quantity and quality of water. The models range from conceptual, empirical to complex, physically based distributed simulations. Scientists run the models under various scenarios of climate change, land transformation, overpumping and mismanagement. However, there are large uncertainties in these projections. The accurate model requires detailed data collecting using advanced techniques such as remote sensing, sensors and isotopes. The models reveal that in some regions hydrological components change mainly due to climate driving forces, while in others dominant factors include direct land conversion and water abstraction. The changes have sharply accelerated in recent decades. Groundwater depletion, altered river flow and reduced recharge are rising in every part of India. During 1980 to 2022, river flow has declined nearly 20 to 50% in some watersheds in Himalaya, Krishna and Godavari basins. Similarly, the rate of groundwater depletion has risen from about 0.15 meter per year in 1980 to nearly 0.5 meter per year in 2023. Dear students, this was all about today's program. Hope you have enjoyed it well. Thank you for watching.